friends, this is Agya Dahal. We have already discussed about the analysis of beams and frames on our previous videos. In this video, I am going to talk about the deflection of the beam. So for finding out the deflection of the beam, there are several methods. Some of them are double integration method, conjugate beam method, moment area method, Macaulay's method, and strain energy method. Before finding out the deflection of the beam, first of all, we need to understand the relation between slope, deflection and radius of curvature. For this, we consider a beam AB. So this is a beam AB. If it is applied with a load or if it is loaded, it will deflect like this. This deflected shape will be in the form of an arc which will subtend a radius of curvature R. So I am going to represent this beam AB on x and y axis as shown in this figure. So this beam AB is deflecting and we are considering a very small portion of the deflected shape that is ds, which subtends an angle d theta, and the radius of curvature is r, which is as it is. Now from the extremes of this infinitesimal length we draw perpendicular bisectors. So from the point E, we draw perpendicular to the x-axis, which is at a distance x from the origin, and at a distance y. And from the point F, we draw another perpendicular bisector, which is at a distance x plus dx from the origin, and y plus dy in the y-axis. So these are making an angle theta and theta plus d theta. This dx is a small length, and this ds is also a very small length. Now we are going to find the relationship. For this, I need to understand certain relation. We know theta is equal to arc length by radius. So here the arc length is theta is d theta, arc length is ds, and radius is r. From this we get the value of 1 by r equal to d theta by ds. I'll write this value here, 1 by r equal to d theta by ds. Now, from this triangle, this small triangle, this angle is also theta. So, the value of theta will be dy by dx. Sorry, tan theta will be dy by dx. So, I'm going to write tan theta equal to dy by dx. Now, I'm going to find out the relation of sec theta because I'm going to need, I'll need this later. So sec theta is equal to h by b. So here h is ds and b is dx. So sec theta is equal to ds by dx. This we are going to need later in our proof. So we have got dy by dx is equal to tan theta. If I take derivative of this, it will be d square y by dx square equal to d by dx dy by dx. So this dy by dx is nothing but tan theta. So tan theta. So this is the differentiation with respect to x, but we are getting theta here. So we need to apply chain rule of derivative. So d by dx into d theta by d theta, I'm going to multiply on both sides tan theta. So it will give me d by d theta tan theta and d theta by dx. Now the derivative of tan theta will be equal to sec square theta. Now d theta by dx, we don't have any relation with respect to this. So this also we are going to convert d theta by ds into ds by dx. I'm multiplying ds in both up and down. So this will be sec square theta. So d theta by ds is nothing but 1 by r, and ds by dx is nothing but sec theta. So this will be equal to 1 by r sec cube theta. Now this sec cube theta can be written as sec square theta to the power 3 by 2. So this will be equal to 1 by r. So sec square theta is nothing but 1 plus tan square theta. This will be equal to 3 by 2. Now it will be 1 by r, 1 plus tan theta is nothing but dy by dx. So d square y by dx square power 3 by 2. So I have got here d square y by dx square. So if I take this 1 by r here, I'll get d square y by dx square 1 plus d square y by dx square power 3 by 2. As we take a very small length, we can ignore this d square y by dx square as it is in the form of powers of 3 by 2. So this value is negligible. So we can get, which implies 1 by r is equal to d square y by dx square. Now we all know about the bending equation. So from the bending equation we have m by I equal to f by y equal to e by r. I'm not needing this, so I'll take only this two. So this will give me 1 by r equal to m by ei. So I get m by ei equal to d square y by dx square. So if I need the slope, I will integrate it. So it will be dy by dx, that can be written as theta, equal to integration of m by ei. And if I need the deflection, I'll further integrate it. So that will be y is equal to double integration of m by ei. So with this, I have derived the relation between slope, deflection and radius of curvature. Thank you for listening.